The answer that we are going to see today is that the question is why are local optima dangerous? We are going to answer to this question today. Let us start with an example. In 1996, NASA's NASA's Mars Climate Orbiter was lost. It was a $327 million spacecraft. Not because of a software crash, not because of hardware failure, but because of the navigation algorithm. What the navigation algorithm was doing, it was confidently converging on the wrong answer. So it was giving wrong answer, that too confidently. So it had found its answer. It was certain, but it was wrong. So it was certain, but it was wrong. That pattern, an algorithm becoming certain, stopping its search, and being completely wrong, has a precise name in optimization. It is called trapped in local minima, or in this case, in general, we call it as optimum. It can be local maxima or minima. Better to use the word optimum. And it is the single most dangerous failure in all of optimization. Not dangerous because it crashes loudly, but because it fails silently. So the failure is silent. So you will feel things are going fine, but it has failed. So today we are going to understand exactly why this happens, what makes it so hard to detect, and why it is the core problem that the entire field of metaheuristics was built to solve. So, a reason for the existence of metaheuristics. So, to understand the local optima, we need to talk about how a search algorithm moves through the solution space. Almost every classical algorithm works by same principle. It starts somewhere, it looks at its neighbor, then it tries to see the solutions which are reachable by a very small change and to move to whichever neighbor is better. And this is repeated until no neighbor is better than you. Right. So if there is a person, he sees who is doing better. Suppose he's getting certain marks in exam, then he sees his neighbors and he tries to align his strategies with the neighbor who is successful. So almost every classical algorithm works by the same principle, that they start somewhere, they look at the neighbors, and by making certain small changes, it tries to reach to that neighbor or become like him. So this strategy is known as the hill climbing strategy that we have seen before also. That valley climbing if you are minimizing all those things. So it is simple, fast, and works perfectly on a smooth unimodal problem. So it is fine when the problem is unimodal. I talked about this modality of the problems in one of my videos before. So, anyways, every step it improves the situation. This is the target. Now, the catastrophic failure cases is when the landscape has more than one valley. We saw in another case where the terrain was multimodal. Now, the algorithm it works downhill, finds a valley floor, and looks at all its neighbor and sees that they are all uphill and concludes I'm done. I found the optimum. But it has only found the optimum of its local neighborhood. Somewhere else on the landscape, completely unreachable by the downhill steps from here, is a deep valley. Is a deep valley. So the global optimum, this is the global optimum. But how will the algorithm find it? He doesn't know. For him, like it is like a fishes in the aquarium, they don't know about the ocean, right? So because for reaching here, first of all, you have to go here. But the algorithm says never go uphill. So this is against the principles of the algorithm to go uphill, right? It has compared with the neighbors, they are all up, and it will never proceed towards that because, like I said, we are going to the person who is better. So this is not a quirk of a algorithm. It's a fundamental property of any search related method that it uses a greedy local improvement, which includes gradient descent. Gradient descent, hill climbing, steepest ascent, etc. The only search strategies that are immune to local optima are the ones that can accept a temporary worsening. So that little bit problem, this algorithm, if it is ready to accept that, okay, let us go a little bit uphill and let us see what happens. Suppose it has got that flexibility that can go uphill to eventually find a deeper value. And those strategies all belong to the family of meta heuristics, which is exactly why we are studying them. So here is what makes the local optima uniquely dangerous compared to other failure modes. That is the algorithm, it doesn't give you any warning. No warning. So algorithm, when it is here, at that time, it will just conclude that I found the best solution. Right. So you have to remember that when an algorithm crashes, when it runs out of memory, okay, when it produces, when the algorithm crashes, we know it. When it runs out of memory, we may know it. When it produces an infeasible, impossible solution, we know it. We can check all of this. But if it finds the local optima and it behaves in every way like it has succeeded, then what happens? The convergence curve looks smooth. The objective value stops improving exactly as it would if you had found the global optimum. So the indicators they suggest that you have found the best answer, the result is returned, everything looks fine. So this is a problem. Let us take one example, the detection problem. Why we cannot tell from inside? Suppose our algorithm it converges to an objective value of 47. This is the objective value. Now, how will we say that the number 47 is a good optimum or we have succeeded or 47 is a local optimum and the global optimum is 31. How will you know it in the first place? From inside the algorithm, we cannot tell. The algorithm has no access to solutions outside its neighborhood. It cannot compare itself to unseen regions of the landscape. This is why the researchers run algorithms multiple times with different random initializations. Multiple times with random initializations. Compare against the known benchmark optimum, uses statistical tests across different runs. The detection of the local optima is empirical, not algorithmic. Means we cannot depend on the algorithm. Sometimes it is about the empirical nature of the problems. So there is a useful analogy from everyday life here. Imagine you're searching for a cheapest flight to a city. You open one travel website, find a price, book immediately. Did you find the cheapest flight in existence? Certainly not. You found the cheapest flight that one website showed you. To find the true minimum, you would need to check every source, which takes lots of time, and that time you might not have. An algorithm trapped at a local optima is doing exactly this. It found the best option in the small neighborhood it explored. The vast majority of the search space that is potentially containing better solutions was never visited in the first place. So, what is the real engineering cost? So, suppose if we talk about the antenna design, we are seeing one use case. The engineers optimize the geometry of the antenna arrays to maximize the signal gain across the frequency range. The parameter space, the length, the angle, the spacing between the elements is highly multimodal. Early optimization tools using gradient methods regularly converged to a local optima that looked acceptable. But meta heuristics, when meta heuristics approaches were applied to the same problem, solutions were found with improvement in the decibel gains. In decibels, 3 decibel means double the power. That entire gain was invisible to the local search because it sat in a region that algorithm has never visited. Then we can talk about drug molecular design. In this, computational chemists search for molecular configurations that bind strongly to a target protein. The conformational space of even a mid-sized molecule has thousands of local energy minima, stable configurations where the molecule settles. A gradient approach finds whichever minimum it starts near. But a configuration with the strongest binding, that is the global optima, global optimum, might require the molecule to adopt an initially unfavorable intermediate shape before reaching the best binding pose. So algorithms that cannot tolerate temporary worsening will never find it. So it is not their cup of tea. So these are some of the examples that we saw. Now let us add a precise concept that explains why certain local optima are so hard to escape. That is the basin of attraction. Basin of attraction. Every local optimum has a basin of attraction, the set of all starting points from which a greedy hill climbing algorithm would converge to that local optimum. Think of it like a drainage basin on a map. Every raindrop that falls inside the basin flows downhill, and eventually it reaches the same lowest point, the local minimum at the center of the basin. The size of the basin of attraction is critical. The local optimum with a large basin is extremely dangerous because no matter where you start your search in that region, you will be pulled toward it. Even multiple random restarts will land in the same basin, converge to the same wrong answer. A local optimum with a small basin is less dangerous. It only captures starting point very close to it. The random restart is likely to land outside the basin and converge somewhere else. So these situations are more dangerous. We can see. This is why random restart running the algorithm many times from different random starting points is one of the simplest escape strategies in these scenarios. If the global optimum basin is large enough, eventually a restart will land inside it. But random restart is expensive because again and again, if you keep on starting your algorithm, it is expensive. It multiplies your computation cost by number of restarts. If the global basin is genuinely small, you might need thousands of restarts to hit it by chance. This is why smarter escape mechanisms, the kind that is built in the meta heuristics, like when to start the um, exploitation, having adaptive inertia weights, genetic mutations incorporated. This helps us avoid the scenario. So I hope we are clear with this concept.